Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former Professor and Head of the Department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series intended for the optics, especially on the phenomenon of diffraction of light. And you know that the diffraction is a phenomenon which could be explained only on the basis of wave theory of light. And in the earlier lectures we saw the diffraction which is due to a circular aperture and then due to a circular disc, and the contents of this lecture will be the cases wherein we will see the diffraction at a narrow slit, then the diffraction patterns for a narrow and wide slits. We will start with diffraction due to straight edge. What do you mean by straight edge? You can have a plate like this. This is a light beam that you have got here. This is a straight edge. That is, the part of the light beam is cut off. If you have a source of light here and you have got a screen here, you have got a screen and this is a source, light is coming and incident on the screen, light is seen on all the walls, there is no obstruction. Now what you do is you obstruct the light beam by means of straight edge. It is straight, right? Straight, you know, you cut off the light. You got the screen here, you cut off the light. Now what do you observe? As I told you in the last few lectures, if you would have believed in Newton's theory, the corpuscular theory of light, this region, because you have got light here, this region below this should be perfectly dark, because the light is cut off. Okay, the light is cut off. So the region below this should be perfectly dark, and above that there you should have uniform intensity. Both these things do not happen. Above this the intensity is not uniform, below this there is no darkness. You know, here you should have geometrical shadow. You know, you do not allow light to come through. The obstacle is an obstacle in the sense it obstructs the light going from the source to the screen. It completely obstructs means what? You should have a dark shadow region here, and there should be uniform brightness. Both these things do not happen. In the region where you should have uniform brightness, certain other things happen. Similarly, in the place where you have got a geometrical shadow, it is not complete shadow. You have a pattern, you have got diffraction pattern, interesting patterns that you see here, which also I have seen shown earlier also, the kind of diffraction pattern. So I will show straight away what happens before going through the discussion. It will be more interesting to see the diffracted images that you are getting due to the case of straight edge. You got a plate, as I told you, you got a plate here in the path of the light beam. If Newton's theory would have been followed, then the entire region below this should be dark because the light is obstructed. Above this, there should be uniform intensity. Now, what really happens is light has wave-like characteristics. So, what is diffraction? Diffraction is nothing but the bending of the light beam. You know, diffraction is nothing but the bending of the light beam. As shown in the diagram, the light beam bends. You see the bending, right? The bending of the light beam. So, because this bending, what happens is you got a source of light, you got an opaque object. This is the opaque object. You have the source of light, you got an opaque object. Below this, I should be having uniform darkness, and above that, I should be having uniform brightness, right? That should be uniform brightness and uniform darkness. In the region below the geometrical shadow also, you have got kind of diffraction pattern, and above the region, above the object space, you have a diffraction pattern, right? According to the older theory, now what should be happening is this light, this will be completely dark and this will be completely bright. In the region where there should be brightness, you have a diffraction pattern, you have got diffraction bands. You see here interesting thing. I told you in the earlier lectures, right, when I started diffraction, if you have a blade, you have a blade in the path of the light beam, you can have this light beam and carefully look at the blade. At the edges of the blade, you will be getting a pattern. This kind of pattern can be seen by naked eye. A naked eye, you can see this kind of diffraction pattern, that is the bending of the light beam around the obstacles, that is the diffraction pattern. This is the interesting picture. You got a source here, you got an opaque object, you have the screen here. In this region around the edge of the object, it is a straight edge. You got an edge here, straight edge. This is the region around the straight edge. Around this edge, right, is the edge, the center of the edge here. Below this, you don't have, this region, around this region, you have a pattern, this kind of pattern, right? And this, of course, you don't expect normally, and similarly, this also you don't expect if you believe in the older theories. This is what is happening. This is the so-called diffraction that is happening in the case of straight edge. Now, what I would like to tell you is, in the region here, right, the intensity is not uniform, very near the edge, right. And older theories, there should be uniform intensity, but here inside the geometrical shadow as well as outside, the intensity will be intensity of light as a function of distance from the edge of the geometric shadow. The intensity is not uniform, it varies like this, right, and it falls off. Then after that, the intensity will be uniform. After this means what? You go above this, you have a, you got light here. After all, in this region there will be uniform intensity. This kind of bands will disappear and the intensity will be uniform. You will have uniform intensity, but near the obstacle, near the edge of the obstacle, certain unexpected things happen. As I told you, near the edge of the blade, this kind of pattern will be there. If you have a blade, far off from the blade, nothing will be there. Near the edge of the blade, there will be lines which could be seen. You see this, the lines, the diffraction pattern. Similarly, near the edge of the shadow, edge of the geometrical shadow, edge of the opaque object that you are keeping here, you have this kind of pattern. Far away from this edge, you go here, there will be uniform intensity. That is what I am showing here. The intensity will become uniform. You see the intensity changes. Very near, you see here, bright, dark, bright, dark. They are the so-called diffraction bands. Now, let me ask you straight away a question. Now, how will you compare these bands, the so-called diffraction bands, with the interference bands? You have seen the interference bands which are produced by the double slit, the Young's double slit experiment, or Fresnel biprism, or Newton's rings. Unlike the intensity will be uniform, every bright ring will have the same intensity. The dark region also will be equally dark. And again, you have what you call a bandwidth. What is bandwidth? distance between two successive bright bands or dark bands is called the bandwidth in the case of interference bands. But here you see the distance between the two is this much. The distance between these two is coming smaller. The distance between these are they are decreasing. The intensities are also decreasing. You see the intensity here is large. It comes down. Then thereafter there will be uniform intensity. Okay. So the interference bands are different from the so called diffraction bands which I am showing here. Now let us go to a theory, right? The some kind of monotonous theory should be there. Otherwise you cannot have quantification. You can see the pictures, but you have to have some quantification of maybe this kind of diffraction can be used to determine the thickness of the wire, about which I will be talking in the time to come. Here we are talking about diffraction at a straight edge. Let S be a narrow slit illuminated by a source of monochromatic light of wavelength lambda. Anyway, this is a kind of edge you are talking about, the pattern that you got here. So, where is the P, the point source? When you are talking about the straight edge, so I am showing the straight edge once again. You are having light passing through the edge here, right? So, S is the source and P is the point we want to find the intensity. Similar to the earlier case also, we go to another point P prime. There also we want to find the intensity. How will you find the intensity at the point P? This is a straight edge, right? This is a straight edge because I showed just now you got light, the source is here, you have the edge here, right? The edge, straight edge. I want to see I have the screen here, what is happening at the point P, right? And P prime. Even at P prime, at P or below P, there should be inside the geometric shadow, you have got a shadow region. Because the light is obstructed, there should be shadow. Within the geometric shadow, there should be complete darkness. But what you find this interesting thing is inside the geometric shadow, you do not get darkness, but on the other hand, you have this kind of this is a straight edge. Okay, this is the geometric shadow. Inside the geometric shadow also there is light. Okay, the interesting point is this is a obstacle. There is a source of light. You got obstacle here. When you got obstacle, you should be completely cut the light. This is the and you should have complete shadow means darkness. That will be complete darkness. Instead of darkness, you got a certain amount of intensity of light. It is there. It becomes 0 after some distance, and above the geometric shadow, there should be uniform brightness. What happens to the brightness? You do not have uniform brightness. As I showed you just now, the intensity changes, right? There is intensity, right? There is a graph drawn between intensity and the distance. So, above the obstacle, this is the obstacle which obstructs the path of light beam. So, when it obstructs in the region where there should be uniform intensity, because there is nothing there, there will be uniform intensity of light. But on the contrary, you get a pattern called the diffraction pattern. A diffraction pattern is one wherein the intensity starts differing. The intensity of light is so much, then the next you get a diffraction band with this much intensity. Next one, the intensity of the diffraction band, it comes down, and thereafter, as I told you, intensity becomes 0. The intensity becomes uniform, right? Thereafter, the intensity, it is uniform, right? This kind of variation is not there. These variations refer to what? They are the diffraction bands. They are the diffraction bands. The first point is the intensity of the first band is not equal to second band, third band. The intensities of the successive bands starts changing, decreasing, unlike the case of interference bands. That is point number 1. I will come to the second point after the break. Welcome back to the break. We have been discussing the case of the diffraction pattern that we will be getting when light is hitting a straight edge. A straight edge is something like a metal plate or a cardboard that comes in the path of the light beam, wherein within the geometric shadow you get light which is unexpected, because light should be cut off, because light behaves like waves. You have a certain amount of light in the shadow region, that is important, geometric shadow region. Second thing is, above this, instead of uniform intensity of this much magnitude, this is the intensity axis, you get bright and dark lines, or you get a diffraction pattern. I told you the intensities of the bright lines, right? They are the dark lines. The intensity of the bright line, the second bright band, third bright band, the intensities are decreasing. Similarly, dark bands also, you see the dark band, they are again decreasing, number one. The second point, as I told you, where I stopped before the break, is that distance that separates the two bands, that again changes. You see suppose you call the bandwidth, right? Where is the bandwidth here? You call this in the case of interference bands, the distance separating two successive bands is the bandwidth. So, you have two successive humps, but the distance between the 6th or 7th hump and 8th hump is almost very small, negligibly small. Therefore, there is nothing like bandwidth in the case of diffraction. Again, the intensities will not be same, the first band, second band, third band, whether bright or dark. These points should be kept in mind when you compare the diffraction bands with the interference bands. Let me now pass on to the theory part, namely we are trying to understand as to how we could explain the formation of the intensity changes that you see outside the geometrical shadow and a finite intensity within the geometrical shadow. So, P is a point on the screen, SAP is the perpendicular screen and all these things. As I told you, the distance is B. What is the distance? The distance is B, and you got P here, and with this as the pole, to explain the changes in the intensity, as we did in the earlier cases, we have to draw or construct the half period zones. So, with P as the center, as we did long back in the case of rectilinear propagation of light, the same diagram we used, we drew the first half period zone with B plus lambda by 2 as the radius. You were able to draw a sphere, then P plus 2 lambda by 2 with that as the radius, you were able to draw the second sphere, and so on. These spheres which you construct, they will be cutting the xy, that is what is called the wave front. The xy is the wave front, they will be cut, and so in 2 dimensions you will be getting what are called half period zones. So, the important point is, in the case of diffraction, whether it is straight edge or wire or aperture, circular aperture, whatever be the case, you will be constructing what are called half period zones, without which you cannot explain the intensity variation. That is number one. The second point is, you should have in mind, we are talking about, we are using the Fresnel diffraction here throughout my lecture series. From all the diffractions that effects that we have seen, they come under the class Fresnel diffraction and not Fraunhofer diffraction. Fraunhofer diffraction makes use of lenses. Here I am not making use of lenses. There are finite distances separating the source and the obstacle and the screen. Distances are finite, and so I am making use of Fresnel diffraction. And as I told you, with P as the center, we have constructed the half period zones. Okay. Then, so xy is the wave front. Okay. A is the pole of the wave front. AM1, okay, these things, all these things are known. AP is equal to B. So, now what I do is, with B plus lambda by 2, B plus 2 lambda by 2, then 3 lambda by 2, I draw spheres. They cut the wave front and they result in the off period zones, and the light coming from the off period zones along with the obliquity factor, both of them should be taken into account. Whether you have odd number of zones or even number of zones, with these things in mind, we have to calculate the intensity at a given point. Okay. So, Pm1 is equal to B plus lambda by 2. This is P, this is M1. Pm2 will be B plus 2 lambda by 2. Okay. There are things that you all know by now. So, you get what are called half period strips. The important points I want to emphasize. Now, we are not constructing half period zones. Now, they are called half period strips. That is important, that I have underlined somewhere here. So, we are talking about half period strips, that is important, right. Why because you have a strip, right, you have got a strip here. So, we will be constructing what are called half period strips. M1 is a half period strip, M2, M1 is here, M2 is here, M3 is here, and so on, right. They are the half period strips. You have a cylindrical wavefront that is being considered here, and you have light is coming through the region here, and so the cylindrical wavefronts are constructed into half period strips and not zones. Okay. Let P prime be a point on a screen in the illuminated portion. To calculate the resultant effect at P prime due to the wavefront xy, let us join S to P prime. This line meets the wavefront at B. B is the polar wavefront, all these things will depend. So, the intensity at P prime will depend mainly on the number of half period strips, right. It is not zones, half period strips enclosed between the points A and B. Where are the points A and B? So, you have got A and B in the A is here, and you have got to find out how many. The AM1 is the first cylindrical strip, the M1, M2 is the second, it is not half period zone, half period strip. So, the light coming from the first strip, second strip, these things are to be considered to find the intensity at P, and similarly intensity at P prime. Okay. They are the half period strips. So, again you have to look for the even and odd. The effect at P prime due to the wavefront above B is the same at all points on the screen, whereas it is different at different points due to the wavefront between B and E. The point P prime will be of maximum intensity if the number of period strips enclosed between B and E is odd, and the intensity at P prime will be minimum if the number of period strips enclosed between B and E is even. I told you that the odd number of strips and even number of strips. So, supposing you got 3, what will happen? The resultant displacement will be M1 minus M2 plus M3. If you have got only 2, it will be M1 minus M2. If you have got only 2, what will happen? M1 minus M2 will be minimum. On the other hand, if you have got M1 minus M2 plus M3, then it will be maximum. Therefore, depending upon whether you got 2 or 3 or 4, 2 will be minimum, 4 also will be minimum, 3 will be maximum, 5 will be maximum. So, the number of strips that you have got, either odd or even, that decides the intensity that you determine at a particular point. Okay. If a point below P and B is the new pole of the wavefront with reference to the point P prime, then the off period strips below B are cut off by the obstacle, and only the uncovered off period strips above B will be effective in producing the illumination at P prime. So, whenever you have a straight edge or any kind of thing, some of the strips or some of the half period zones will be cut off depending upon the point where you want to find the intensity. As P prime moves farther away from P, more number of period strips above B is cut off, and the intensity gradually falls. Because the intensity falls off, then thereafter there will be uniform light. A number of period strips above B is more number of period strips cut off, the intensity gradually falls off. I showed you the intensity variation. Intensity will be going like this, maximum, then minimum, and the second maximum will be lesser than first minimum, and then thereafter the intensity variation will be much smaller. Thus, within the geometrical shadow, what happens? You get some light. The intensity gradually falls off depending on the position of p prime with respect to p, the intensity distribution on the screen due to a straight edge has been shown, and you have them S is the source, AD is the straight edge, M1 is the screen. So, you got here S is the source, this is the source of light, this is my straight edge. I consider two cases. One is the point P. Point P is when exactly in straight line with respect to source. What about P prime? I will ask the question, what about the intensity at P prime? Whether P prime will be dark or will you be getting some light? I will tell you that even though P prime is a point inside the geometrical shadow, there will be some intensity. Intensity does not become 0, and more importantly above P there will be what are called diffraction bands. Okay, that you should be having in mind. As I told you just now, below P you have the geometric shadow. Within the geometric shadow there is some intensity, okay, unlike what you would have expected according to earlier theories. And again above P you do not have uniform brightness against the older theories. You do not have uniform brightness, you get a pattern wherein the intensity starts changing, right, that the intensity variation is there. They are the so called diffraction bands. So, you explain the diffraction bands using half period strips, you are constructing half period strips. Okay. In the illuminated portion PM, right, this is the illuminated portion PM, alternate bright and dark bands of gradually diminishing intensity will be observed, and the intensity falls off gradually in the region of the geometrical shadow. So, let us look at the geometrical shadow. It falls off gradually, that is geometrical shadow region. Above the geometrical shadow region, the intensity goes up and down, the intensity rapidly changes, then it acquires a uniform intensity. That is what I am trying to tell you here. The illuminated portion PM alternate bright and dark bands of gradually diminishing intensity will be observed, and the intensity falls off gradually in the region of the geometric shadow. Thus, according to wave theory, the shadows cast by obstacles in the path of the light beam are not sharp. According to Newton's theory, they should be sharp, and hence rectilinear propagation of light is only approximately true. This is what we have seen in the earlier lectures also. The rectilinear propagation of light is only approximate. Okay. Let me now summarize as to what I did in this lecture. The points are: diffraction at a straight edge refers to light obstructed by a plate. The intensity inside the shadow region is obtained by constructing half period strips instead of half period zones considered in the earlier cases. The diffraction bands will have decreasing intensity unlike the interference bands. There is nothing like the term bandwidth. The questions that you have are the following: what do you understand by diffraction at straight edge? Comment on the intensity distribution of the diffraction pattern and also compare it with that of interference pattern. With this, we come to the end of the lecture on diffraction at a straight edge. The other cases we will take up in the lectures to come. Thank you.